All right, so today really marks a transition in this course. So everything we've dealt with for the past few weeks has been trying to find the external forces that are acting on some object or some structure. So days 9 and 10, the big days of this class dealing with rigid body equilibrium, was finding the support reaction forces that are developed based on what's going on in my object. And that's important. So I want to know all the external forces acting on it. One of the reasons why I want to know all the external forces acting on it is because those external forces create some internal forces, and those internal forces are really what is going to determine how strong my structure is, so how much weight it can hold, whether it needs to be built out of steel or wood, because these things all have different inherent strengths. How big of a piece of wood can I use? Can I use a 2x4? Can I use a 4x8? And so that really gets into the next class, mechanics and materials. But the first step in that is figuring out what these internal forces are. And so days 9 and 10, as I mentioned previously, probably the most important days of this class. These next 2 days, today and next class, kind of follow close behind that, because again, these are things that you'll be doing in future classes, trying to find the internal forces. So we have 2 different ways to do this. 2 different methods, each have their own advantage and disadvantages. So today we'll be dealing with something called the method of joints. But first of all, I'm going to kind of describe what we're actually doing here. So usually when we do these methods of joints or method of sections, we're looking at some sort of big structure. So something to hold up a whole lot of weight, something like a bridge or a roof. And those are usually made out of these kind of triangular patterns. If you ever crawled up your attic or looked at a bridge, usually have some triangles involved. The reason for that is because a lot of times we can assume any connection is a pin connection. So anything that's connected will allow some rotation. So if you're going to allow some rotation and you come along and push on it, this thing without triangles is just going to start to fall over, and that's not a good thing. So the triangles stop that from happening. So that's why I usually see triangular patterns in these big structures, like these bridges. And so even though these structures are inherently 3-dimensional, they have cross members, we usually only care about the 2-dimensional plane, because we can kind of assume that the forces are kind of distributed evenly throughout that 3rd dimension. And that way we can just look at just a 2-dimensional version of it. And so what we're trying to do here is actually find the internal force on each member. So what we've done previously is find these reaction forces. So in this case, for this bridge, I have some pin connection at one end, some roller on the other end. I can then find my 3 external reaction forces based on the external loading. And now what I want to do is come and look at, okay, how much force is in each one of these members. So this angled member here, how much force is in that one? How much force is in this horizontal member down here? How much force is in this vertical member? And so on and so on. So every one of these members, I want to know how much force, how much internal force is acting inside of it. And again, that's the first step to knowing what I need to build this bridge out of to make it safe. So there's one really, really big assumption we're going to make both today and next class. And that's that every single member is assumed to act in pure tension or pure compression. What that means is that the internal force inside of it goes in the exact same direction that that member goes. So if we go back to this previous diagram here, this horizontal member up here has only a horizontal internal force inside of him, absolutely 0 internal force in the vertical direction. Same thing for this vertical member. Only has a vertical internal force, no horizontal ones. Same thing for this angled one. Whatever angle this is, that's the exact same angle that the internal force acts. So again, big assumption we need to make is that every internal force is pure tension or pure compression. So tension just means that it's pulling. Compression just means that it's pushing, but it's pushing or pulling in that same direction. For this one big assumption to be true, we need a lot of smaller assumptions to be true. So the first thing is that the members are linear. So each member itself is a straight line. If the member was a curved line, there'd be no way to have a force that's also curved. Forces are straight lines. So the members have to be straight lines too. The member is connected by pins. So again, that's the assumption we're generally making. The member weights are negligible because if a member has some weight, that weight's going to be like a distributed load acting along the length of the member, generally going to be a uniform load. And that's, as we know, can be replaced by a single load in the middle, but I don't want any forces in the middle. I only want forces to be applied at the joint. So this kind of lines up with the fourth assumption here, that every external load has to be applied at a joint. And the reason for that is, so you see here, all these loads are applied at joints. If I had a load that was applied in the middle of a joint, so like the member weight, what that would do is it actually slightly bend this. So again, depending on how much force that is, but that actually bend the member slightly. And if my member is bent, it's no longer linear. And so then I can no longer have a purely tensile or compressive force in it. So basically these four little assumptions kind of all lead up to this one big assumption that all my forces go in the same direction as the members. And so in real life, as I mentioned, a lot of connections that you see in truss structures, you have all these members bolted to some gusset plate, and that actually kind of acts as pin connections. So this assumption of having pin connections makes sense in real life in terms of what actually happens. So that's one of the reasons why we're doing that. So tensile and compressive forces, as I said, go in the exact same direction as these members. So if I have a vertical member, my tension force is also vertical. Tension is like a rope pulling. So tension pulls on things. If you have a rope pulling on something on one end, you have an equal and opposite force pulling on the other end. So that's a tensile force. Same thing with compression, just opposite. So compression pushing on something. If I'm pushing on something on one end, I have to push on it equal and opposite force on the other end for it to stay where it is, for it to be in equilibrium. And so this actually leads to a different sign convention, as we're going to see, because up to now, we've been dealing with left, right, x direction, positive, negative, up, down, y direction, positive, negative. As you can see here for tension, I have two forces, one going up and one going down. For compression, I also have two forces, one going up and one going down. So because these forces are equal and opposite, they add up to zero. There's actually going to be a different sign convention we'll be using, and going to be using two sign conventions at the same time, which confuses a lot of people. But that's just because external forces follow the old rules. Internal forces have their own rules. And what that rule is that tension by convention is positive. So any force that pulls on both ends is a positive internal force. Compression, therefore, is negative. So any force that pushes on both ends of the object is negative. So as we've seen, a lot of trusses are made out of triangles. If you have a structure that's made out of a whole bunch of triangles, that's called a simple truss. So you can see down here, the triangles don't need to be the same. They can be different triangles, but as long as you can make a structure out of a whole bunch of triangles, those are simple truss structures. And some types of trusses are used very commonly, so they have special names, like a Pratt truss, Howe truss, and Fink truss for typical roof trusses, so different members going in different directions to hold up whatever load you have. Some bridge trusses, so very similarly Pratt and Howe, so vertical and angled members. I have a Warren truss, which is all triangular. And some fancier ones, K trusses, Baltimore's. Some stadium truss structures, cantilevers, bascules, so all sorts of trusses that you may have seen before. Again, the point of this is to find all these internal member forces. So that's kind of the overview of what we will be doing the next couple of days. Specifically for the method of joints, what we're going to do here is if I have a structure and it's in equilibrium, that means that each individual part of my structure is also in equilibrium. So instead of looking at the whole structure, I can just look at part of it and use the equations of equilibrium on that one part. Specifically for the method of joints, it's going to be at each individual joint. So because each individual joint is in equilibrium, instead of looking at the entire structure, I only have to look at that one joint. And each joint is where members come and connect to each other. And because we made this assumption that all my member forces go in the same direction as the members, all the forces go through that one point. So I basically look at each individual point, and that's going to be a concurrent force system. So no forces acting way off at a distance. They're all coming through this one single point. Because of that, there's going to be no rotation involved. So there's no moment equation here. All I have is the lateral sum of forces in the x direction, sum of force in the y direction equations. So instead of what we did a few days ago using 3 equations of equilibrium, I'm only going to have 2 for each joint. But I can use those 2 equations to find up to 2 unknowns. And those unknowns that I'm talking about are the actual internal member forces. So at each joint, if I have 2 unknowns or less, I can solve for those internal member forces. So general procedure for method of joints is to construct the free body diagram of the entire structure. So a lot of times the first thing I need to do is what we did on day 9 or 10 and actually find the external forces that are acting at the supports. So I'm going to have a roller on one side, a pin on the other side. And first thing to do is what we did on day 9, find those external forces. So free body diagram, find the forces. And then once I have all my external forces found, here's where the method of joints really starts. I want to just take one single joint and isolate it from the rest of the structure. So just look at that one single point. Again, I want to look at a point that has less than 3 unknown members coming into it, because if I have 3 or more, I can't solve them. Remember, I only have 2 equations of equilibrium for each joint. So force in X and force in Y. So I need 2 or less members that I don't know the internal force in. When I have that one single joint, I can then just draw the free body diagram. Again, replace all my members with some internal force for that member, and then use my equations of equilibrium, force in the X direction, force in the Y direction, and I can solve for those 2 internal member forces. Then once I have those, I can move on to another joint with hopefully less than 3 unknown forces, and use a new set of equilibrium equations for that new joint, and then so on until I've gone through the entire truss structure and found every single member force inside of it. So again, if you look at one of these trusses here, I'll look at this Pratt truss over here, have a pin connection, have a roller, so replace those with external forces, do rigid body equilibrium, find what those values are, and then good places to start for this guy would be either at the pin or at the roller, because at this point, I'll have some external reaction force from the roller, I'll have some internal force from this horizontal member, and some internal force from this angled member. So those are my 2 unknowns. I can use forces in the X and Y direction equal to 0 to solve for those 2 unknowns. Then once I have those 2 unknown, or they're now known, internal member forces, I can then move on to another joint, say this one down here, because this one down here, I know this force, but I have 2 new unknown forces in these 2, the horizontal and vertical members. I can then find those 2 using new set of equilibrium equations, force in the X direction and force in the Y direction. Now I know this internal member force. I've already found out this internal member force. So up to this joint up top here, I now have 2 ones that I know, 2 ones that I don't know. So again, force in the X direction, force in the Y direction, solve for those guys, and kind of just carry on until I'm all the way to the other end and I've solved for every single reaction force. So as you can imagine, this is a fairly lengthy procedure. So during class today, we'll go through at least one example. I can guarantee that much. Hopefully get 2 more, but as you said, it does take a while. So hopefully we get through a few of them today.